Today we want to introduce some other coordinate systems. In particular, we want to relate this to our work with double and triple integrals. So this is other coordinate systems plus double and triple integrals. We're going to start describing R2 in a slightly different fashion. That is with polar coordinates. All right, so let's review rectangular coordinates. We start off with an origin, and we label all the points in R2 with an X and a Y coordinate. X is the horizontal distance from the origin to the point, and Y is the vertical distance from the origin to the point. And so that's how we locate points in R2. The thing that we want to note, thinking in terms, looking ahead to double and triple integrals, we are using two distances. X and Y are both distances. So this would be like X meters and Y meters. These are both distances. I always say length. I decided this semester to switch to distance. So I'm going to try, but I'm going to devolve into length. The reason that I don't like using length is because in a triple integral, dx, dy, and dz are all going to be lengths. And so those are all going to be distances, but one is length, one is width, one is height or depth. It doesn't really matter what we call them. But the thing we want to note here is that both coordinates represent a distance. And these are rectangular coordinates. The other way we can describe every point in R2 is with polar coordinates. So the other way we can describe points, all the points in R2, is with polar coordinates. So if we have a point out here in two-dimensional space, we'll say that this coordinate, the coordinates of this point are r and theta. R is the distance from the point to our pole. The pole is located at the origin because we wanted to make things easy on ourselves, not difficult on ourselves. So r is just the distance from the pole to the point. So this is the distance r. Theta is the angle in standard position. So we need more than just a pole. We need to know where the positive x-axis is so we can decide from where to measure the angle. Here's the angle theta. We need two pieces of information to describe points in two-dimensional space, just like your address has two parts to it, a house number and a street. For some cities, both can be numbers. We usually don't say negative though, we'll just go like east and west. So like east would be positive, but instead of saying positive Fifth Street and negative Fifth Street, we'll just say East Fifth Street and West Fifth Street. What we want to notice in polar coordinates is that, once again, we're still using two pieces of information to describe all the points in two-dimensional space, but one of them is a distance, the other one is an angle. We're using a distance and an angle. One coordinate represents distance, one coordinate represents an angle. Let's talk about why I'm pointing this out. It comes to, when we think about double integrals, if we think about the integral over R of some function of x and y, dA. We know that dA is a little rectangle piece of R. dA is a small rectangular piece of R. PIE? It's a small rectangular chunk of region R. It represents a piece of area. dA is dx times dy. dx is some small length, dy is some small width, so dA is some area, some small area. So what we're doing here is just area is equal to length times width. This is the thinking that we built up behind setting up a definite, a double integral. This works because x is a length, y is a length, so dx is just a small length, dy is just a small length, everything is fine. In polar coordinates, it's not so fine. So if I set up a double integral in polar coordinates, dA is still a small rectangular chunk, almost rectangular chunk of the region R. dA still wants to be a small chunk of the region R. The problem shows up if I try to break up dA in the same way we broke up dx, dy. So if we write dA as dr times d theta, now we have a problem. dA is supposed to be an area, dr is a length, but d theta is a change in angle, not a width. So that's the problem that we run into here. dr is a length, that's okay. But d theta is not a width. It's going to be an angle in radians rather than a length in meters, for example. So I can't say that dr d theta is some small area in the region R, because d theta is not length. We wouldn't end up with area units. Dx dy, it's no problem. Length in meters, width in meters, area in square meters. Length in meters, angle. Meters times radians. And radians, they don't show up, so it's just meters. Not helpful. We need to turn this change in angle to a length. That's what we run into now. The change in angle needs to become a length. We need to take this d theta and somehow make it into a distance. We need d theta to be a distance so that dA can be an area. So here's how we're going to do that. So let's say I've got some point and it's at a distance r. So here's r. And then we want some small change in r. I'll make that delta r, some small discrete change in r. That's where delta r shows up, which eventually becomes the dr. That's where dr shows up. It's a change in length. If r is in meters, then delta r will also be in meters. The problem that we have is that theta, or the d theta more importantly, is going to show up as an angle. This little tiny gigantic angle that I'm drawing. That's what d theta represents. It's not a distance. But I want the area of this little segment right here, the area of this little piece. Everybody see the problem? I want to make sure that everybody recognizes the issue. dr or dx dy is length times or distance times distance. That gives us an area. I want dA to represent an area. dr d theta, not good enough. dr is distance, d theta is angle, which is not distance. It's the wrong units. I need to turn d theta into an angle. So here is a picture of the rectangle or the little dA chunk that I want of my region capital R. So first thing we're going to do is we're going to notice that it's not exactly a rectangle. If you thought, are we going to treat, but we're going to treat it like a rectangle, then you are correct. We're absolutely going to treat it like a rectangle. Even though this side is curvy, this side is curvy, and this outer side is longer than the inner side, right? It's not a rectangle. But if we make delta R small enough and we make delta theta small enough, it'll be close to a rectangle. And that's what we want. So the first thing to notice, not quite a rectangle. dA is not quite a rectangle, but if dr and d theta are small enough, it'll be close. That's always the thinking that goes along. Make things constant on a short enough interval, and that'll be good enough. Then just make the interval shorter. What we need to do is get this green length. We notice that this green length is r units away from the origin. So we'll just use arc length. And we'll say that d theta we'll just say arc length is going to be the change in angle times the radius. So we're just going to build the arc length with r times d theta. Most of the time we use S to represent arc length because I don't know. Maybe this is why M is slope, because we've used S for arc length. So that's what we're going to use for dA when we write our double integrals. We can't just use dr d theta, but we're going to use the arc length S as the length and dr as the width. So dA will be r times d theta times dr. So this extra factor of r makes dA into a length. Sorry, this extra factor of r turns d theta into a length, and that gives us dA as an area. So our double integral over some region of a function in polar coordinates, dA dA will be r d theta dr. That extra factor of r is not part of the function. We put that there. We have to integrate it now. It's now part of the function that we integrate, but we put that there. That extra factor of theta turns d theta into a length so that r d theta dr can be an area. And then we just have the values of theta and then the values of r. Now the rules for double integrals still apply. The outer integral has to be constants. The inner integral can be functions of upcoming variables. When we go to integrate, we still integrate the function with the r in it. But that factor of r came from the dA part. R d theta dr, this is our dA. Any questions? This is important to realize because all we're doing when we start using more these different coordinate systems is we have to describe, when we go to three, we're going to use three distances, that's rectangular coordinates. We'll use cylindrical coordinates, which is two distances and an angle. And then we'll do spherical coordinates as one distance and two angles. That way, if we go into 4 dimensions, we could use 4 distances, or we can use 3 distances and 1 angle, 2 distances and 2 angles, 1 distance and 3 angles. We can't do all angles because similar triangles and stuff. Any questions? How's everybody okay? Too simple? It always takes me too long to say stuff, so. Let's use this to find an area that we already know, like a circle. So we're going to describe the circle to a double integral in polar coordinates. Let's say that the circle is a circle of radius r. We know that for dA, we need r, dr, and d theta. And the way I've set it up here, I've put my theta first, and r is going to be second. The outer integral needs to be functions of the upcoming variable. Sorry, the outer integral needs to be constants. The inner integrals, the early integrals, can be functions of upcoming variables. This means that r has to be constants theta can be functions of the upcoming variables. So theta can be functions of r, but r has to be constants. We look at any value of theta. For any theta, we want the r's starting at 0 and ending at capital R. Should have just picked a number. Why couldn't I just pick a number? I guess I did pick a number. I picked capital R. Now we need to get all the thetas. All the thetas where we go from 0 to R. So for all the thetas, I need to start off with the x-axis. I need to go all the way around the circle. So theta is going to go from 0 to 2 pi. So here is a definite integral describing, or a double integral describing this circle of radius r, centered at the origin. The reason we have that extra factor of r in the r dr d theta dr, that r turns d theta into a length. That length turns dA into an area. Remember that if f of r theta is equal to 1, this will give us the area, should give us the area of the circle. So if we integrate from 0 to r, the integral from 0 to 2 pi of 1 r d theta dr. First thing we'll do is we'll integrate with respect to theta from 0 to 2 pi. So this will be the integral from 0 to r of r theta from 0 to 2 pi. So this is going to be the integral from 0 to r of 2 pi r minus 2 pi times 0 dr. Now, if we integrate the 2 pi r with respect to r, we get pi r squared evaluated from 0 to r, where 1 r. If we integrate for 2 pi r with respect to r, we get pi r squared evaluated from 0 to whatever the radius of the circle is. The interesting thing here is that in rectangular coordinates, 2 intervals gives you a rectangle. In polar coordinates, 2 intervals gives you a circle. So if, for example, we wanted to just describe the integral, the quarter circle in the second quadrant, we would use the integral we would still integrate r from 0 to r, but we would just adjust our theta for the second quadrant. So theta will just go from pi over 2 to pi. And that would give us this quarter circle in the second quadrant. Note that in rectangular coordinates, this would be more complicated because in rectangular coordinates, we have to describe a round thing with square coordinates. Not that it's impossible, it's just messier. In rectangular coordinates, the relationship what we're dealing with is x squared plus y squared is equal to big R squared. And so we could solve for y as plus or minus the square root of big R squared minus x squared. So in a double integral, we wouldn't have the r, we could still just go dy dx. This time x would have to go from negative r to positive r, and y would go from negative square root to positive square root. If we try to use these rectangular coordinates and calculate the area of the circle, we would end up integrating 2 times the square root of r squared minus x squared. And all of a sudden, our integral, instead of just being add 1 to exponent, divide by exponent, we have to do trigonometric substitution, and everybody is sad. Until we realize that we're doing trigonometric substitution on a definite integral. We don't need the antiderivative in x. We have a definite integral. Do the substitution to theta, change the endpoints to your new variables, and then integrate there. You don't need the antiderivative in x. Incidentally, I wonder where we end up if we did that. So if you're not sure what I'm talking about, you do the same thing. If f at xy is equal to 1, then we get area. So here's our definite integral. The first integration that we do is dy. So we integrate from negative r to r of y, evaluated from negative square root to positive square root. We plug in the endpoints, and we're integrating from negative r to r of 2 times the square root of big R squared minus x squared dx. And at this point, we make a sad face. We say, oh man, this is trigonometric substitution. And my TI-84 can't do it because there's an R squared, not a number. So we do sad face. But we press on because trigonometric substitution is in fact our favorite. And this is sine case. So x is r sine theta. So dx is r cosine theta to theta. We know what's going to happen in the square root parts, but then we have to recognize that this is a definite integral. So when x is negative, when x is negative r, then negative r is equal to r sine theta. That is, sine theta is equal to negative 1. And when x is positive r, then r is equal to r sine theta. And so sine theta is equal to 1. So we could use this to figure out what values of theta we should integrate over. Now you may be noting this is giving us from this one is the pi over 2, and this one's giving us the negative pi over 2. That's only going to be half a circle if we go from negative pi over 2 up to pi over 2. Why is that not going to be a problem here? Because notice that this is going from theta equals negative pi over 2 to theta equals pi over 2. That's only a half a circle. That's only quadrant 1 and 4. Why is it not a problem that we're only getting half the circle when I integrate from negative pi over 2 to pi over 2? Because I got the 2 in front of the square root. Lucky us. That 2 is going to take this half circle and double it. Any questions? All right, that's gonna do it for today. Tomorrow we'll talk about the other two types of coordinate systems. It's just this plus the z-axis and then kind of spherical coordinates, which is different. That's it for today. I'll see y'all on tomorrow. Thanks for playing. See you tomorrow.